max for any gn is going to be 1 because it's always going to be non-zero. That's equal to 1. And that will always stay at 1. So this is always 1 for all.
Because now we have also measure 0.
Nice.
0. It's good to know the issue
Because
it does that.
yeah, it just doesn't change because it's always a positive.
That's like the high power.
Yeah, exactly. No matter how close it is to 0, there's still that peak.
Well,
What was it?
we know because
I was sworn in.
we have
Okay, so it's down to 0 as soon as it got close.
so we take to 0 apply the extreme value theorem.
Yes, if you watch the
It's just a line, so it doesn't line. So you just apply the extreme value
Give me the
theorem.
animation again.
Yeah, here we go.
The extreme value theorem, sorry.
As it gets close to 0.
It's gonna be over there.
gn has to go to
Nothing.
infinity.
Like for any point bigger than 0,
Mm-hmm.
right, you can always pick some in that makes it sort of go up and then down before it.
Yes, okay, so this is the thing, right? So these functions, I think that you've exactly found the observation. So gn, we're only looking on 0 to 1.
Oh.
And the point is, on 0 to 1, maybe this was a detail that was not missed. We're only thinking about the function on 0 to 1. Maybe I should have made the Desmos only live on 0, 1. But on 0, 1, no matter what x value you pick, so if you pick the x value, x equals 0.2, I'm going to do a point. 0.2 comma 0, right? So you're like thinking about that x value. No matter what x value you pick, eventually the spike kind of shrinks past it, right? So no matter what x value you pick, eventually that spike is to the left of the point you picked because the spike is shrinking down to 0. So, and at that point, once the spike is completely to the left of the point you were thinking of, then not only is the function converging to 0, it's actually equal to 0. And it's like equal to 0 forevermore after that. So this is the reason why it's converging pointwise. For any fixed point, eventually the spike is to the left of that point, and then you're at 0. Not only are you converging to 0, you have arrived at 0 and you're there forever. So it's a very strong type of pointwise convergence. So most people figured out that it was going to 0. Who thinks they would be confident in getting full marks on the midterm if it said, explain why it's converging to 0 pointwise? Okay, not many people. Okay, so this is good to practice because there is a difference between sort of getting the mathematized right, I think most of you are on the right track, and understanding the reason why. So make sure you know that. Actually, why don't we practice? Let's write it up then. This is worth writing up so that we can have a good practice of that. So Fn, I think actually they were called Gn. Okay, Gn is the function of x, is this piecewise function 2 to the n times x, or 2 minus 2 to the n times x, 2 to the minus n times x? No, 2 to the n times x, or 0 if x is bigger than 2 times 2 to the minus n, 0 less than x less than. Okay, and I guess these should be equals, and 2 to the minus n less than or equal to x. Okay, so it's this spike function that looks like this. So here's the axes, and we're living on 0 to 1, and it has a spike, and then it comes down. The center of the spike is at 2 to the minus n, and the edge here is 2 to the times 2 to the minus n. Okay, and so we're going to do a claim that Gn of x goes to 0 pointwise. Okay, and here's the proof. So we want this idea that no matter what point you pick, eventually the spike is to the left of you. So let's start with what we want is that it's going to 0 pointwise. So we say for any x in 0, 1. And actually, and now that I'm writing it down, this is one of the advantages of writing down the rigorous proof in math. The thing that I just said is that for any x, eventually the spike is to the left of x, is not literally true. It's only true for most x. There's one x where it's not true. Yeah?
X equals 0.
X equals 0, yeah. So the thing I said before actually is only true if x is not equal to 0. So we can add a little disclaimer here on the first line. If x equals 0, then Gn of 0 equals 0, which obviously converges to 0. Right? Obviously, Gn of 0 converges to 0. So that's good. So if x equals 0, we're covered. We've covered our bases. If x is bigger than 0, then what do we want to say? We want to say eventually there is a value of n so that the entire spike is to the left of x. How do we translate that into math? If x is bigger than 0, then I claim that we can find, let's say, capital N so large so that what? Well, we want the entire spike to lie to the left of x. Like we're sort of thinking in our head. X is here, and the entire spike is to the left of x. Well, the edge of the spike is at 2 times 2 to the minus n. So what I would like to have is that 2 times 2 to the minus n is less than x. And I want that to be true for all n bigger than n. So that is a true fact. Like eventually it's going to happen. Is there a way we could justify to the reader of the proof, whoever is reading the proof, if they said, well, why is that true? Could we give them a nice like one-line reason why it is true that 2 times 2 to the minus n is eventually less than x? What would you say if somebody asked you, why is it true? Yeah.
As n gets big, that shrinks to 0.
Exactly. Yeah. So I would say this thing is a quantity whose limit is 0, and therefore it will be eventually less than x. So you could say, maybe I like these kinds of things like in brackets, because the limit as n goes to infinity of 2 times 2 to the minus n equals 0, and that's less than x. That's like a nice little way to cover your base in case the reader is like, well, I don't know why that's true. So that's a really nice way to do it. And this is the kind of thing where if this was a calculus 1 class, we would spend a lot of time on why is it true that the limit is that. But now we're just assuming like we can do those limits, and we're using them to build up bigger things. So you definitely don't need to justify more than that. Okay, so 2 times 2 to the minus n is less than x. And then you could say, by the definition of g, of gn, we have gn of x equals 0 for all n bigger than n. And that is exactly by the definition of g. If you wanted to be even more clear, you could say by the third piecewise part, right? You could say because gn of x equals 0 for x bigger than 2 times 2 to the minus n is the third piece. Okay, and if gn of x equals 0, then of course it is converging to 0. Since gn of x is equal to 0 for all n bigger than n, limit as n goes to infinity of gn of x equals 0. And you could finish with a nice little underline to show you're done. That's kind of like a mini QED. Okay. Let me see. Can I make the whole thing fit on one page? There we go. So that's probably more detail than you really need, but that covers all the bases. Any questions or comments about that proof? Okay, fantastic stuff. I'm glad we went over it. Okay, that was pointwise convergence. There's 2 other types of convergence that are on the page. Let's take a look at those. And let me open up the right thing. Okay, here it is. Okay, that was pointwise convergence. Can I just reveal counts again? Or will it? L1 convergence. And I want to reveal. That's pointwise. Okay. So click on this. I scroll up here. Okay. So this one, again, 10 to 2. People think it goes to 0 in the L1 norm. And just like before, this is correct. So if you said L1 norm, then you got it right. This one maybe is easy. I don't know if this one is easier or harder than the pointwise one. It depends on how much you like norms. So yeah, what do you guys think about this one? Is this one? Let's do a vote on easier or harder. Who thinks this one is easier than the other one? Hand up for easier. Who thinks harder? Okay, harder. Okay. The reason it seems harder is because you guys haven't seen norms very much until last class. So once you get the hang of norms, this one will seem easier. But let's do it together. Yeah, question here.
I know about things. If I can create a function that is like non-zero for a finite set of points,
Yeah.
it would be have the 0 norm under that,
Yes.
but it wouldn't be the 0 function.
yes, this is a great, we're going to get to this later, so you're like 2 classes ahead. So it turns out, if you want L1 to be a norm, L1 is not a norm on the space of functions, exactly because there are some functions which are not exactly 0 but have integral 0. So to make L1 an actual norm, what you have to do is you have to look at the set of functions with equivalence up to being screwed up on a set of a tiny couple points. So we say that functions, if they're equal to 0 except for like 5 points, we just say that's the 0 function. It's indistinguishable from the 0 function. And by doing that, we make the L1 norm an actual norm. For the purposes of this question, you could say the L1 norm is a thing that is not a norm. So it's something we calculate and we talk about convergence, but it doesn't satisfy the axiom that if the L1 norm equals 0, then it's the 0 function, and we're going to fix that issue later.
Okay.
Yeah, no, this is a great question. Okay, so let's do this one. Let's do it, since you guys seem a little worried about it. Let's do it the nice long way and really explain it up. So the claim is that Gn goes to 0 in L1. And Gn going to 0 in L1, the definition of that, so this if and only if arrow means, all I have to do is I have to verify that the norm of Gn goes to 0. And maybe I'll do one thing here. And this is one thing, in the textbook, they never write any vector signs. And 0 sometimes means the 0 vector, and 0 sometimes means the 0 number, and you just have to know by looking at the things that are nearby which is which, okay? And this is like how math is written because people are too lazy to write vectors everywhere. But I sometimes will write the vectors for you to try to help you out. There should be a vector here. Why should there be a vector here? Because this function Gn, we're thinking about it as a vector in the normed vector space, which is functions equipped with the L1 norm. So that's a normed vector space, and we're talking about it converging to another vector, which is the 0 vector. The 0 vector in this space is the function, which is always 0, the 0 function. So even though it's a 0 vector sign, that is the function, which is always 0, which lives in the space of functions. It's the 0 function. On the other hand, on this line, you have to know we're talking about numbers. So this is the 0 number, like the number you learn about when you're in kindergarten. So the absolute value, or the norm of Gn, the norm is something that is a number. So Gn is a function, and the norm of Gn is a number. And this is a sequence of numbers. The norm of G1, the norm of G2, the norm of G3, these are all a sequence of numbers, and we're just talking about the sequence converging. Does that sequence converge to 0? So this kind of question, other than it being the norm of a function, which is new to this class, it is a sequence of numbers, and whether or not a sequence goes to 0, that's something you do in calculus 1 again. So basically, to check if the functions converge in the fancy complicated vector space, you are reduced to a calculation of checking if the numbers converge as a sequence. So all we got to do is calculate that thing and argue why it converges to 0. So let's do it. So proof. We can calculate that the norm of Gn is equal to what? So the norm of Gn, let's write down the formula. It's the integral from 0 to 1 of the absolute value of Gn of x dx. But Gn is always positive, or at least non-negative, I should say. So it's just the integral of Gn. You'd say G, since Gn is positive. Okay. And because it's positive, we can actually just say this is the area under Gn. So you could kind of do it really algebraically and take the integral from 0 to 1 and start using the piecewise definition and write out all the parts of the integral. That would definitely be one valid way to do it. But I'm going to just go with it's the area, and the area under Gn is the area of a triangle. It's the area of a triangle. Area of a triangle of width 2 times 2 to the minus n and height 1. So you can see that from the picture. Maybe I'll redraw the picture over here so I don't have to scroll away, right? This was Gn of x, and we're just looking at the area underneath this triangle, which is this stuff. So it's a triangle. The width here is 2 times 2 to the minus n, and the height is 1. Okay. And I know the formula for the area of a triangle. It's 1/2 base times height. So 1/2 2 times 2 to the minus n times 1, which is 2 to the minus n. So the area is a very nice number, 2 to the minus n. and the L1 norm is just the area in this case, because it's never, if it was negative and positive, then you would have to worry about when is it negative and positive, but this function is always positive, and so the norm is just 2 to the minus n. And so now we're reduced to proving that this sequence of numbers goes to 0 is the same as proving that the sequence 2 to the minus n converges to 0. And that's a fact that we can just say. And we all know that it works. And in fact, we used that in our last proof, right? In our last proof, we used this fact that the limit was 0. So we say since limit as n goes to infinity of 2 to the minus n equals 0, therefore limit as n goes to infinity of gn of x equals 0. And I don't put norms, I really mean it as numbers. And then we're done. Okay. Questions or comments about that one? Yeah.
So for any arbitrary norm, the definition of converging under that norm is that the limit as n goes to infinity of the sequence in that norm, it goes to 0.
Well, okay. That's the definition of converging to the 0 vector.
If it's 0, otherwise it's a minus.
Exactly, yeah. So if it was gn converging to some other function g, then it would be the norm of gn minus g. And that's literally what it means. Yes, exactly. And that's because the norm is kind of like our distance function. And so in metric spaces, we say the points are converging if the distance between them is going down to 0. That's exactly what we do. Yeah. I really think you should think of it as like we have this like complicated space, and we have equipped ourselves with a meter stick, and that's how we're going to measure convergence or anything else. So any question about convergence, we turn it into a question about numbers. We take a problem which is about vectors, and we use our measuring stick to turn it into a question about numbers, and then we use our calculus 1 skills to see if that sequence is going to 0 or not. Yeah. Yeah.
So just one more thing. Yesterday in class, or on Tuesday, when we defined uniform and pointwise convergence,
Yeah.
it wasn't directly with a norm because we hadn't said which norms there were yet.
Right.
Are those statements just equivalent to using the correct norms?
Yeah, so I believe on Tuesday's class, I said that the version of uniform convergence, which I stated as it converges sort of everywhere. Like there is one value of capital N that works for all the values of x. And I said this is equivalent to converging under this norm. And I didn't prove it. It's a good exercise. And it's not so complicated because the norm is something like the maximum. And so if the maximum is less than epsilon, then every single point is less than epsilon, and vice versa. So it's a good check. It's a good exercise to try to do that. But yeah, I didn't like specifically go through it in class. And you could write a proof exactly like this. Like if the maximum is less than epsilon, then every individual point is less than epsilon. If every individual point is less than epsilon, then the maximum is less than epsilon. You could write it up. Yeah, that's a great point. Yeah, and I guess the thing that's new is I think you guys have seen, or at least have heard of uniform and pointwise convergence before, and now I'm telling you that uniform convergence at least comes from a norm. So that's new, right, to this class. Just the fact that it comes from a norm is new. Okay, great questions. Anyone else? All right, let's do the last exciting part of the problem. Are the GNs, are they going to 0 in the L infinity norm? And wait, you might have, if you were looking carefully, I think I revealed it for 1 second. Let me see if I can go back to hiding it. Okay, great. Okay, so this one is more split. It's 4 to 8. Is it going to 0 or not? Let's have a revote. This is 4 to 8 is close enough. Let's do a revote and see what you guys think. So the majority is on not going to 0, but of course the majority has been wrong many times. So don't go just based on that. Really try to figure it out and think about what it would be like writing up a proof of your claim or whatever you think it is. Okay, so I'll give you a couple more minutes and we'll revote.
Because And that will always stay at 1, so
Because
this
this was gonna be integer.
is always 1 for all
Because
of
now
these.
we have also measure 0. Unmeasured.
Yeah.
Norm
Nice.
0 does that? It's good to know this because
Because-
it does that.
Yeah, it just doesn't change because it's always a positive.
That's like the height part.
Yeah, exactly. No matter how close it goes to 0, there's still that peak.
Well,
What was it?
we know because
I was wondering.
we have
So it went down to 0 as soon as it got close.
so we did to 0 apply the
Yeah.
extreme value
I
theorem.
guess if you watch the
Because there's a lot, so there's a lot. So you just apply the extreme value
Give me the
theorem.
animation again.
Yeah,
What?
here we go.
The extreme value theorem, sorry.
As it gets close to 0.
It's gonna be on the
GN has to go to
That's
infinity
like it works, right?
for the
It's
peak,
gonna
which
be
is at
this one's gonna be
2
17.
to the
One or the other goes to that. That's
minus
it.
9
So
is at 0.
Okay,
Which doesn't
so
happen in the finite.
I reopened it. Hopefully you guys all had a chance to revote. But I think you guys are talking about the right kinds of things. I will say it is true in Desmos. It does, if you look very carefully, it looks like right at the end it starts to shrink a little bit. And that's because Desmos is a crappy computer. Right? So if you actually if you go based on that, I guess you have to know when to trust Desmos and when not to. But if you plug in the point 2 to the minus n, the middle of the peak, then the formula will tell you that it's exactly 1. So any kind of like shrinkage here at the end of the picture is because Desmos is struggling to deal with very tiny numbers and is starting to catch on fire, and not because it's actually less than 1. So, and you can check that from the formula. That's why I gave you the formula. If you plug in, so it's 2 to the n times t. If t equals 2 to the minus n, then you have 2 to the n times 2 to the minus n, which is exactly 1. Okay. Okay, I think everyone had a chance to vote. 11 people, that looks right. Let's see what people said. Okay, so hopefully you guys got the first two perfect right. This is a good way to check if people are awake. Okay. Not everybody. All right. And this time, 11 people are not going to, which is the right answer. So maybe you saw, I think it was on the screen for 1 second. But can someone, this one has a short, like 1 line answer. Can someone tell me why it doesn't go to 0 in the L-infinity norm? Yeah.
Is it because the maximum doesn't go to 0 as n goes to infinity?
That's right. The maximum is always 1, and that's not going to 0. So it's the thing you got to check is the sequence 1, 1, 1, 1, 1, 1, 1. Is that sequence going to 0? And the answer is no. So very good. So this one is maybe the easiest one. The claim is that the norm of Gn infinity does not go to 0. And if it does not go to 0, that means Gn is not going to the 0 vector in L infinity norm. Right? That's exactly what those mean. And the reason, the proof is the norm of Gn infinity equals the maximum of x in 0, 1 of Gn of x, which is 1. I guess might be even easier to just say it's greater than or equal to 1 and not worry about proving equals, because Gn of 2 to the minus n equals 1. So by finding one point where the value of the function is equal to 1, that technically just proves that the maximum is at least 1, right? Maybe there's some other point somewhere that has an even higher value. Of course, in reality, it doesn't. But to minimize the number of things I write and the number of things I have to convince the reader of, I'm just going to write just that. And so that does not go to 0. Okay, as a sequence of numbers, if you have a sequence that's always bigger than 1, it cannot possibly go to 0. Okay. Great. This is a really good, like, hands-on with the kinds of things we're going to be doing in this course, and the kinds of some of these will be on your homework and the midterm. So let's pull this back up. Any questions or comments about this one overall? Yeah.
Will it converge to 0 if it's L2, L3?
Yeah, this is a really great question. And there's a question like this on your homework. But that question, so the question on your homework is not for functions, but for sequences. And in sequences, it's about infinite sums. But the same answer that exists on your homework problem will exist for these things. So there is an order of these norms where it's possible it can converge for one and not the other, but the reverse will not be true. And I will let you guys do the homework problem. So go do the homework problem, and then we'll know. And we can definitely, I can post the answer to your great question after the homework is due. Okay. Yeah. And yeah, any other questions or comments? Okay, so why are we doing this example? The thing that I wanted to show you, and the whole point of this example is to show you one fact, which is that norms on functions are genuinely different, or can be different. Okay. So in some norms, it's going to 0, and some norms it's not going to 0. And the same kind of thing exists on sequences, that different norms are genuinely different objects that have different convergence properties and will behave differently. This is not true for finite dimensional things. So the thing we're going to work towards in the rest of the class is proving that on finite dimensional spaces, all norms are the same. And I'm going to put the same in quotes, right? Because they're not literally the same. Like, you could take one norm and multiply it by 2. That's technically a different norm. But what do I mean by the same? I mean they have the same convergent sequences. So if something is converging in one norm, then all the other norms, it'll still converge. If something is not converging, then it won't converge in any norm. So there's only one type of norm in terms of sequences. And this is called equivalent. So in the textbook, this is called equivalent. Maybe I will write out what equivalent means in typed math so that it's a little bit more clear, because it's a definition from the textbook. I'm scared to ask it for a new window because it might crash, but okay, we'll try. Let's make sure we save first. Okay. New thing. Okay, and then I want to do. Let's just do this. Okay. Again, these are a bunch of macros that we might use. But so we're going to have a definition of what it means for two norms to be equivalent. And this is definition 1.3.9 in the textbook. Okay. And it says two norms. And so we're going to call our two norms norm sub 1 and norm sub 2. Okay. And so this is a confusing thing in the textbook. When we're doing this proof, we're talking about two different norms. We're calling them norm sub 1 and norm sub 2. So we have names for them. We don't mean the L1 norm and the L2 norm, right? So it's a confusing thing where norm sub 2 could mean the L2 norm in the context, or it could mean the second norm in that problem. Here it means the second norm in the problem. So just heads up for that. So what does it mean? They are equivalent means. What does it mean? It means that xn converges to x in the norm sub 1 if and only if xn converges to x in norm sub 2. So they have the exact same convergent sequences. That's what it means. Okay. Yeah, I'll write it like that. So if you have a sequence and it converges in norm 1, then it converges in norm 2, and the reverse is also true. If it converges in norm 2, then it converges in norm 1. So that's what equivalent means. And we are working towards theorem 1.3.13, which says if V is finite dimensional, then all norms on V are equivalent. Okay. So the thing that you saw with the warm-up example is a genuinely finite, it doesn't happen in finite dimensional spaces. It has something to do with things getting infinitely thin. Like the fact that the spike can get infinitely thin is the thing that enables there to be a difference between the uniform norm and other norms. Okay, and we're gonna start by proving some little results along the way. Well, one result is this one. Theorem 1.3.11. It says two norms are equivalent. Two norms, norm sub 1 and norm sub 2. They are equivalent if and only if there exists constants C so that this holds. Is the 2 or 1? Let's do it with 2. All right, I gotta make this one a 2. Okay, so we said that the definition of the two norms being equivalent is all the sequences are the same. And this theorem says that that is exactly the same thing as the two norms just being within some constant of each other. So the example I gave earlier, I said, what if one norm is just double the other norm? That's the only way the norms can be equivalent. If there's just some constant, so that they're always upper and lower bounded by that constant. So, and it's not that it's always twice, it's like at most twice and at least some lowercase c on the other side. So the two norms cannot be more than some constant outside of each other. It's not like one of them could be some really high norm and the other one is like really going to 0. They're always within some constant factor c of each other. Okay, so let's prove it. And to prove it, I'm going to go to the blackboard, so I could type it up, but I think it shows kind of like how you're thinking about the math to do it by paper. So let's do it. And it's a proof by contradiction, so let's think about how that would go. So, okay, so we're working on theorem 1.3.11, and we want to show that we can find C and C so that C norm x sub 1 is less than norm of x sub 2 is less than C norm of x sub 2. And we are given that the limits are the same, right? Given norm 1 and norm 2 are equivalent. Okay. So we're going to do this by contradiction. So it's a proof by contradiction. Proof. Suppose by contradiction there is no, and did we do uppercase c or lowercase c? Okay, let's do lowercase c. So we're going to suppose by contradiction there is no lowercase c that has this property. Is one of the words hard to read? Yeah.
No, it's the inequality I don't understand. So you have norm 1 and then norm 2, norm 2.
Yes, because okay, this is good. This is a lowercase c and this is a capital C.
Okay.
And so lowercase c could be like 0.1 and capital C could be like 15. And so it's saying that if you know the norm 2 of some vector, let's pretend the norm 2 was 2, okay? Then the norm 1, sorry, other way around. Yeah, okay. Are you just pointing out that I made a typo here? And this should be one. Okay, great.
I couldn't tell if it was a typo or
Okay, yes, no, it's a typo. Very good. All right, I was going to spell it out for you, but I think it's just a typo. Did I get it right over here? I got it right over here. Good. Thank you. Okay, is the statement clear? Maybe I'll finish saying what I was saying. So if lowercase c was 0.1 and capital C was 15, and you knew that the norm 1 was, say, 2, then you would know that the norm 2 is somewhere between 0.2 and 30. Like, you wouldn't know what it is, but it's somewhere between 0.2 and 30. And because they're always like controlled by just some constant of each other, then of course the limits going down to 0 are going to be the same, right? It's like if something is going to 0 and the other thing is between 0.1 as big and 15 times as big, then that's definitely going to 0 as well. But we're trying to prove that that always happens. Yeah.
We're using the same two constants for all x's here?
Yes, that's a very important point. So find C so that this holds for all x in V. That's a very good point. So we want some constant that works for all the x's. Of course, if you wanted it to work for any x individually, you could just make it like the ratio of the norms of that x. So that wouldn't be interesting. Yeah?
Could you give an example of 2 different norms?
Yeah, well, so one is the L, like we just did, the L infinity norm and the L1 norm, right? And the example we saw is that the L infinity norm and the L1 norm on functions are not equivalent, right? Because there was that sequence of spikes that does go to 0 in L1, but does not go to 0 in L infinity. Those are not equivalent norms. And so you will never be able to find these C's. For two norms that are equivalent, you will always be able to find these C's. And so, yeah, so basically if somebody comes along and says, I'm thinking of this tricky norm, and you like do all these weird things, and you like come up with a number, maybe it turns out their norm is just equivalent to L1, and then we just say, like, go away, we don't need you, we just do it the L1 way. And we don't need to worry about that. Yeah, great question. Okay. So let's think about how we prove this. So suppose by contradiction there is no lowercase c. What would it mean if there is no lowercase c? That means no matter what lowercase c you choose, the statement, so no matter what c you choose, so c is in R, the statement for all x in V, C norm x1 less than norm x2 is false, right? That's what it would mean if there is no C. So if there exists a C where this is true, then that's what we want. If that's not true, we're supposing by contradiction there is no C, then that statement is false. Okay, so no matter what C you choose, that statement is false. What does it mean for that statement to be false? Well, the statement says for every possible x something happens. What does that mean for that to be false? It means there exists an x in V, so that C norm x1 is not less than. Not less than is also known as greater than or equal to x2, right? So I negated that statement. So no matter what C you choose, no matter what C in R you choose, this thing is true. So if the statement of the theorem is false, which we're supposing by contradiction it is, then no matter what C you give me, I can always find a vector x that has this bad property where the C times the norm of x1 is bigger than the norm of x2. Okay, how are we going to prove the theorem from here? Well, what do we know? We know something about sequences of vectors, right? We were given that the two things are equivalent, so the limits of sequences are the same, right? The limit as n goes to infinity of x n equals x in both norm 1 and norm 2. Always. Like they have the same limits. So what we're going to do is we're going to use this property. No matter what C you give me, I can always find an x. I'm going to use that to build a sequence x. And I'm going to choose C equals 1, then another C to get x2, and so on. So let's build a sequence using this. So let's build a sequence. And here's the sequence. I'm going to choose C equals 1 over n. And when C equals 1 over n, can find, I'm going to call it xn, so that 1 over n times the norm of x1, the norm of xn sub 1, is greater than the norm of xn sub 2, right? So by choosing C equals 1 over n, C equals 1, C equals a half, C equals a third, I get this whole sequence of vectors that like violate the inequality that I'm looking for. They make the inequality C times norm x1 bigger than norm x2. Okay. Now I'm going to normalize these vectors. So these vectors that you found, xn, they might have any norm. They might be very big or very small. I'm going to look at the normalized version. So I'm going to call these un. So let un be xn divided by norm of xn. So that's a unit vector. And I want it norm 1, I believe. Norm 1? Okay. Let me make sure I want it norm 1. No, I don't want it norm 1. I want it norm 2. Okay, great. Norm 2. So the norm of un sub 2 is always 1. Always. So this is a sequence of unit vectors. And I'm going to do one other thing to them, which is I'm going to divide it by 1 over square root of n. I'm going to call that yn. This is the exact notation from the textbook. So you can also follow the textbook if you want. So yn is 1 over square root of n times un. The norm of yn in the 2 norm is 1 over square root of n. So in the 2 norm, the yns are going to 0 because their norm is 1 over square root of n. So therefore, yn, let's write it like this. The 2 norm of yn goes to 0, and so yn goes to 0 in norm sub 2. Right? So we've made this sequence of vectors, and it has the property. We took the vectors that we were given, we scaled them down by 1 over square root of n, and we set it up so that the yns are going to 0 in the 2 norm. Let's see what the yns do in the 1 norm. But yn in norm 1, what is yn in norm 1? Well, it's greater than or equal to n times the norm of yn sub 2. And that is because they were scalar multiples of how we chose the x's, right? So the yns are some scalar multiple of the x's, and so the inequality that the x's satisfy, the yns will also satisfy. So we could also write because yn is a scalar multiple of xn. Okay, and the norm of yn sub 2 was 1 over square root of n. So this is equal to n, let's do it in blue, n times 1 over square root of n, which is the square root of n, which goes to infinity. So the y-n's, we found a sequence of vectors where the y-n's in the 2 norm go down to 0, they're like 1 over square root of n, and the y-n's in the 1 norm go up to infinity, like square root of n. And so this is a sequence that contradicts the fact that the 2 norms are equivalent. So this sequence contradicts that norm sub 1 is equivalent to norm sub 2. So we found a contradiction. The thing that we assumed that we couldn't find a lowercase c that worked, that must be false. There must be some kind of c that works. And you can do a cool, to end your proof by contradiction, you can do this cool arrow. That's a thing I've seen people do. Okay. All right, I will let you guys think about this for 1 second while I plug the computer in, because we're getting to 20%, which is too low. Okay, yeah, so this is a good, I hear some of you guys asking about big picture stuff. What did we prove so far? We proved that if they're equivalent, then there is a lowercase c, so that c norm x1 is less than x2. There's a couple things left to do. One is, what about the capital C on the other side? So we did one side, what about the other side? Well, the other side would be the same thing. So you switch the roles of 2 and 1, you take the exact same proof, and you apply it again, and you'll get that there's a lowercase c, that's c norm 2 is less than norm 1. Then you just do 1 over c as capital C. So by doing this one side, we get both sides. And the other thing to do would be to prove the reverse direction. So in the thing we're claiming is that it's an if and only if, and we've only done one side. So we said if they're equivalent, then this will be true. The reverse is like really easy. It's the thing about limits that I said. So if the limit of something is going to 0 and the other thing is bounded above and below by c times it, then that also goes to 0. So that one is easy. I think in the textbook they're like, it is trivial. So not that you should get into a good habit of saying that all the time, but it's not hard. So yeah, maybe I'll write these down as a quick note. So I'll say the existence of capital C follows by the same argument, reversing the roles of norm 1 and norm 2. So just do the exact same proof and just replace norm 1 with norm 2. And lastly, so I'll say this proves equivalent norms implies C norm x1 less than x2 less than capital C norm x1. And then I'll say other direction is left as an exercise. Okay. Okay, so where are we? So this is the nice thing. Now we've separated out the battlefield of math where we thought about stuff and did hard stuff with our list of results where we can kind of like see a big picture over here. And so we're trying to prove that things are, if they're finite dimensional, then the norms are equivalent. And of course, that's going to end up being, we're going to hunt down what these C's have to be. And we're going to prove that they exist. We're going to keep going with that. So questions or comments about the proof or about where we're going? Yeah?
In the line where you said C is 1 over n, then we can find a sequence so that that inequality holds true right there.
Yeah.
How do you know that we can find that sequence?
Well, so no matter what C you pick, you can always find an X so that this holds, right?
Oh, okay, got it.
Right?
Yeah.
And so what I did is I picked C to be 1 over n, and I called X n the thing you get when you pick C is 1 over n, so I got this out of it. Yeah.
How did you choose what you let un and yn
Yeah, this is a great question, and I'll tell you the real answer is I read the textbook proof and then I copied that. So how did they do it? I think it intuitively makes sense. You want to pick a sequence of C's that are going down to 0, and then what you're going to do is the C's are going down to 0. That is the factor by which the 1 norm is bigger than the 2 norm. And then what you want to do is you want to do something, you want to make it so that the norm of the 1 norms goes to infinity, but not as fast as the CNs are going down to 0. So that when you do the CN times this norm, together they go down to 0. And so it kind of makes sense that they did CN is 1 over n, and then they did this like 1 over square root of n. That's like the square root of the thing they chose, so that when you multiply them together, it's doing what you want it to do. So the real answer is like copied from the textbook, but it kind of intuitively makes sense to me. You take a sequence going down to 0, and then you scale things so you have like the square root of that sequence. So it's going down to 0, but not as fast. Yeah, that's a great question. Yeah.
Is the UN in norm 2 equals to 1 a constant sequence?
Yeah, well, it's not, the UNs aren't constant, but the norm is.
Okay.
So you can think about it, it's like a bunch of unit vectors. So, and like imagine a sphere, any point on the sphere is a unit vector. So it's like a sequence of vectors on the sphere. They're always distance 1 from the origin, but they're like floating around in some weird way. Possibly. Yeah.
What did we use the UNs for after they were defined?
Oh, the UNs are not even in the original proof. They just went straight to YN. So the point is, I wanted to show you guys this trick of taking a vector and dividing it by its norm. That is a very commonly used trick to get a unit vector. So you start with any vector, you divide it by its norm, now it's a vector of length 1, and then you can like do things to it to scale it to like any size you want. In this case, we made it so it was size 1 over square root of n. So you totally could have just skipped this step. It's just for illustration purposes only. Yeah, great questions, guys. Okay. Okay, so let's do the next path over here, and this is the lemma that kind of makes things work. Or did I want to do? Yeah, okay, you know what? I'm going to save the lemma for when we get to it. So I'm going to start to prove this theorem, and then like halfway through, it's going to be like, now we're going to do this lemma. But that way, I think you'll see like where it comes from. It's a little more motivated than just doing the lemma out of the blue. So let's do the theorem. So the theorem is that any 2 norms on a finite dimensional space are equivalent, and the way we're going to prove it is we're going to come up with a norm and prove that every single norm is equivalent to that one. So we're going to invent on vector space V, on a finite dimensional space V, we're going to invent a norm. It's going to be called the 0 norm. Again, nothing to do with L0 or something like that. So we're going to define this norm, and we're going to prove that all the norms are equivalent to it. What is the norm that we're going to define? We're going to take a basis. So let E1, E2, ... E sub n, where n is the dimension of V, be a basis for V. And this is the thing that you can't do in an infinite dimensional vector space. So in an infinite dimensional vector space, it does not make sense to list out the basis the way we're doing here because it's infinite. But because it's a finite dimensional vector space, this does make sense. And in fact, I think in my notes I called this D for dimension, not n. So let's call it D for dimension. And what is the norm of x0? Well, here's how you find the norm of x0. You take the vector x, you write it as a linear combination of e1 to ed. So the norm of x is the same as the norm of the vector alpha 1 e1 plus alpha 2 e2 plus ... plus alpha d ed for some alpha 1 to alpha d in R. So you write the vector, somebody gives you a vector, you write it as a linear combination of the basis vectors that we've agreed on at the beginning, and then we define the norm to just be the sum of the absolute values. So this is the real definition, alpha 1 plus alpha 2 plus ... plus alpha d. So that's the definition. So if you want to know the norm of a vector, you write down the coefficients, you take their absolute values and you add them up. And this is like the L1 norm on Rn. So this is like the L1 norm on the space R, I guess R to the D, I should say. Okay, so that's the norm, and we are going to prove that every given norm is equivalent to this one. All right. Okay, so first step. And how are we going to do it? We're going to find the lowercase c and the uppercase c. And so here's the first step. So given any norm, given any arbitrary norm, and I guess in the textbook they just didn't write anything for this norm. So we're given an arbitrary norm, consider, and what we're going to do is we're going to say this. Yeah, so the norm of x in the norm you're looking at, well, x is equal to alpha 1 e1 plus dot 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 plus alpha d ed. And now you told me it was a norm. Norms always satisfy triangle inequality. So I'm going to apply triangle inequality to this norm. So less than or equal to, and it's going to be the norm of alpha 1 e1 plus dot 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 plus the norm of alpha d ed. And this is by the triangle inequality for norm. Okay. The other thing that all norms satisfy, this is one of the axioms of norms, is that you can pull out constants, right? So you can always pull out a constant. If you're doing alpha 1 times e1, that is always equal to the absolute value of alpha 1 times the norm of e1 plus dot 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 plus alpha d times the norm of ed. And this is by, some people call this the homogeneous property. The homogeneous property of norm. So these are two axioms of norms. Okay. And now we want to upper bound this by something involving the absolute value of alpha 1 plus alpha 2 plus alpha d. We're allowed to put in a big constant, and I can think of a big constant we can put in that will make sure that this is absolutely less than something involving this. And it's a very silly inequality, but it works. You just do whichever is the biggest. Or why don't we even just do the sum? Let's do the sum. E1 plus E2 plus dot 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 plus ED times alpha 1 plus alpha 2 plus dot 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 plus alpha D. And this constant, we'll call this capital C. And we have shown that the norm of x is less than or equal to capital C times the special norm that we invented, right? The norm x0, which was the sum of the alphas. So if you give me some arbitrary norm, just because it satisfies triangle inequality and homogeneous, it's automatically going to be less than some possibly huge constant times the norm I came up with, that sum of alpha 1 plus alpha 2 and so on. Is there something on the board that's hard to read? Do let me know. Yeah.
I'm just wondering if should C not be the one with all the constants? Maybe I'm reading. Is the stuff on the left, is that all the alphas or is that all the e's?
So these are the e's. Yeah, okay, this is great. Because the e's do look a lot like alphas. Let's be a little bit more clear. So these are the e's, and that's why it's two things, right? These are a bunch of vectors, and I took their norms. And I added all the norms together, so that's some number.
Okay.
And over here is the alphas, which are numbers in R, and I took their absolute values. And yeah, unfortunately, my E and my alpha look a little similar, so it's an unfortunate universe we live in. Okay. For a number of reasons. Okay. So that's some constant capital C, and that's, it always works. No matter what x is, this constant capital C works for every single x. So that's the bigger side. Now we got to do the lower side, right? We got to now must find. It remains to find a lowercase c, so that what? So that c times the norm of x0 is less than the norm of x, right? And in the textbook, they package this up as a little lemma. So in the textbook, this is called lemma 1.3.12. So let me write out the statement of that lemma, and then we will prove it. Lemma 1.3.12, which is if x1, x2, L dots, all the way up to xn are linearly independent, then there exists a constant c, so that what? So that c times the absolute value of x1, nope, the c times the absolute value of alpha 1 plus all the way up to the absolute value of alpha n is less than or equal to the norm of the linear combination alpha 1 x1 plus all the way up to plus alpha n x n. Okay. So it's basically exactly in the middle of our proof of theorem 1.3.11. We need to find a lowercase c, and they just packaged it up as its own little lemma. They said there must be some lowercase c that works. Okay. So we're going to prove it now. Are there any questions or comments about the proof? So I hope you believe me that once we've proven this, then we found the uppercase c and the lowercase c, and then we've proven that the norms are equivalent. I think I might have misspoke a few times and said 1.3.11 when I meant 1.3.13, which is that the norms are equivalent. You guys with me so far? Any questions, comments? Okay, so let's find this lowercase c. How do we find the lowercase c? So must show that there exists c so that c times the absolute value of alpha 1 plus all the way up to alpha n is less than x1 alpha 1 plus all the way up to xn alpha n, and this is all packaged up in that lemma. This is the statement of lemma 1.3.12. Okay, so I guess we went from calling them e's, which were a basis, to x's, which are independent things, but they're the same idea. Okay, so how are we going to prove this? The first thing to notice is that without loss of generality, that's what WOLOG stands for, without loss of generality, we can assume that alpha 1 plus all the way up to alpha n is equal to exactly 1. Why can we assume that the alpha 1 plus alpha 2 plus all the way up to alpha n is exactly equal to 1? Well, if it wasn't equal to 1, you could just divide by whatever that number is on both sides of the equation. So you could say, because let lambda equal alpha 1 plus dot 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 plus alpha n, and prove the result for alpha 1 over lambda, alpha 2 over lambda, dot dot dot, alpha n over lambda. So by dividing, so I guess this is all the alphas. Alpha is equal to. So by dividing through by the sum, you can kind of just like shrink things down so that the sum of the absolute values is always 1. And it works because both sides of the equation are homogeneous, right? If you multiply a constant to every single alpha on the left-hand side of the equation, because of the homogeneity of the norm, it will also multiply on the right-hand side of the norm, and they'll just cancel out. So proving it times 2 or divided by 2 doesn't do anything. This is homogeneous. Okay, so that's the first thing. We're going to assume that the sum of the alphas is exactly equal to 1. By the way, there is one particular special case of alphas where what I said does not work. It was just like, again, tiny technical hiccup. Maybe you noted. Yeah, 0. If all the alphas are 0, you cannot divide by lambda. On the other hand, if all the alphas are 0, what does the inequality say? It says 0 is less than or equal to 0. That one is definitely true. So we can assume this is true. This is if lambda is bigger than 0. If lambda equals 0, the inequality is trivial. It will always hold. Okay, there we go. Okay, so how are we going to do it? We are going to define a function. This is, again, hearkening back to first year calculus. We're going to define a function called f. And f of alpha 1, alpha 2, all the way up to alpha n is going to be equal to the norm of alpha 1, x1, plus all the way up to alpha n, xn. And this is a function which goes from Rn to R. So it's a function that it inputs n numbers and it outputs just one number in R. And it's some norm. In fact, it is a continuous function. F is continuous. So we're going to define this function f, and then we're going to notice it's continuous. Why should this function be continuous? Well, again, it's because of the axioms of the norm. So the norm satisfies triangle inequality. And so if you mess with the coefficients alpha a little bit, like if you make a small change in the alphas, then it can't be that the norm changes by a lot, because that would violate triangle inequality. So you can even prove that it's Lipschitz continuous. It's actually who has heard of Lipschitz continuous? Put your hand up if you have heard. Okay, put your hand up if you've never heard of Lipschitz continuous. Okay, let me tell you what it is for people who haven't heard. So I'm going to do f of alpha 1 plus delta 1, alpha 2 plus delta 2, and so on, all the way up to alpha n plus delta n. So I'm saying, what would happen if you mess with the coefficients by some size delta, right? So you mess up with alpha 1 by delta 1, and so on. Well, that would be the norm of alpha 1 plus delta 1 times x1, all the way up to alpha n plus delta n times xn. And now I'm going to use triangle inequality. So I'm going to take all the alphas and deltas and I'm going to split them apart by using the triangle inequality for the deltas, for the norm. So this is less than or equal to alpha 1 x1 plus all the way up to alpha n xn. And I'm going to pull all those deltas out all by themselves. And this is plus delta 1 times the norm of x1 plus absolute value of delta 2 times the norm of x2 all the way up to delta n times the norm of xn. And you'll notice that this thing on the right hand side here is f. So what I've actually proven is that if you do the difference, f of alpha 1 plus delta 1 all the way up to alpha n plus delta n minus f of alpha 1 all the way up to alpha n. So how much does f change when you change it from being all alphas to adding some perturbation delta 1 to delta n? How much does f change? Well, it changes by at most the size of the perturbation you did. x1 plus the size of delta 2 times x2 all the way up to delta n times xn. Okay, and this is exactly the definition of what it means for a function to be Lipschitz continuous. When you mess with it by a vector, it doesn't change by more than some multiple of the vector. So in general, Lipschitz continuous is something like, I'll do this in a different color. This is the definition of Lipschitz continuous is that f of x plus delta minus f of x is less than or equal to L times delta. And usually people put absolute values. So that would mean it's Lipschitz continuous with constant L. And our function, we have basically that. We have it in Rn, and the Lipschitz constant depends on the norm x1 to xn. So maybe it has a very large constant, but this is a type of continuity, and you can use this to prove that it's continuous. When you go to prove the epsilon delta limit of this thing to show it's continuous, you can always choose delta to be L times epsilon, and it will work. So this is a type of continuity. I will say in the textbook, they just wrote it's continuous and it's obvious. So all of this stuff is extra. I don't know if you guys want me to be more pedantic or less pedantic, but I'll wrap it up there unless you have questions. Yeah?
Is L just a constant?
L is some constant. It's called the Lipschitz constant of the function. And it tells you sort of like what is the maximum possible slope of the function. All right. So functions that are not continuous, it's one way they're not continuous is because their derivative is sort of infinity, right? But Lipschitz functions with Lipschitz constant L, their derivative, if it existed, would always be less than L, and they're definitely continuous. Yeah. Okay. Other questions? Yeah.
So is L defined as the maximum derivative, like the maximum possible
Yeah.
derivative?
If the function was differentiable, then L would work. The people mostly use this for functions that are like very jagged. So like you could have a function which is not differentiable anywhere, but is Lipschitz continuous with Lipschitz constant 1. And then any argument you would make, like you're like, oh, I want to pretend this function is differentiable. It would be so nice if the derivative was less than 1. You can still like make that argument just by using this inequality without ever using the fact that it's actually differentiable. So that's why people use this stuff. Yeah. So it's kind of a way of saying like bounding the function without having to have the function be smooth. Yeah. Yeah, great question. Anyone else? Okay, so if you believe me that the function is continuous, we have one more step to do, which is if the function is continuous, it satisfies the extreme value theorem, and the extreme value theorem says that there must be a minimum value of the function. So by the extreme value theorem, and this will be the very last thing we do, this will complete the proof. By the extreme value theorem, f achieves a minimum on the set alpha 1 plus dot 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 plus alpha n equals 1. So that the set of alphas where alpha 1 plus alpha n all add up to 1, that is a bounded set in Rn, right? It's some kind of like simplex in Rn, right? You cannot escape this region, and therefore the function f achieves a minimum on that set. The minimum cannot be 0. The minimum is greater than 0. Is strictly greater than 0. Okay, this is, I want to put an exclamation point because it's exciting, but you can't put it near the 0. Okay. The minimum is greater than 0. Why is the minimum greater than 0? If the minimum was equal to 0, then the norm of alpha 1 x1 plus alpha n xn would be exactly 0, and then that means that vector would be 0. But we were told that the x1s to xn's are independent. So the minimum is greater than 0 because if it was equal to 0, then alpha 1 x1 plus dot 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 plus alpha n xn is the 0 vector contradicting independence. So this is the point where we use independence of x's. So the minimum cannot be exactly equal to 0 because of the independence of the x's, and that minimum value is exactly the lowercase c that we're looking for. So c equals the minimum value on the set alpha 1 plus dot 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 plus alpha n equals 1 of f of alpha 1 to alpha n works. And that's exactly because our definition of f, right? F was exactly the absolute value. The definition of f is exactly the norm that we want. So if this is greater than or equal to c, that proves the inequality that we want. Okay, so that finishes the lemma and finishes the proof. And this shows you that if you're in a finite dimensional space, all the norms are equivalent. And the thing we saw at the beginning of class, that you can have two functions that are converging in some norms and diverging in other norms, that is a purely infinite dimensional phenomenon. Okay, so next class we're going to start with point set topology, like open sets, closed sets, compact sets, things like that. If you're a little rusty on that, you might want to do a little bit of review, and we'll take it from there. Okay,
Yes.
see you guys on Tuesday. Have a great weekend.